Hello everyone, my name is Ahan and today I'll be presenting you my project report on the topic development of a flexible 3 omega thermal probe for curved surface and soft surface applications. So moving on to the first slide, so the very first question is what is the 3 omega method, if you may ask. So the 3 omega method is a technique that accurately measures the thermal conductivity and diffusivity in various materials, and it is especially used in thin films and bulk solids, and it uh, calculates the thermal conductivity and diffusivity by detecting the temperature induced voltage oscillations at 3 times the input frequency. So it is kind of like an electrical circuit, and we'll get to that later on in the presentation with the circuit diagram. And it is an experimental method used for measuring the thermal conductivity, and this method relies on the principle of heating a sample using a periodic heat source, and it uses a AC current and measuring the temperature response through a sensing technique. So uh, so this is the working principle for the 3 omega method. So initially, uh, as it was mentioned earlier, that it uses heating from a periodic source. So for that, it uses a AC current I at frequency omega, which is driven through the metal heater, and that thing causes joule heating in the temperature plate, which also acts as a thermometer. And this joule heating, it oscillates at it causes the temperature to oscillate at 2 omega frequency, and then ultimately the resistance R mixes with the driving current I uh, at the frequency omega to create a measurable voltage signal V, which is 3 omega. So the third harmonic voltage is inversely proportional to the sample's thermal properties. So this is how basically the process, like one after the other, it follows up, and then in the end the third harmonic voltage is found out to be inversely proportional to the sample's thermal properties. So that is how those two things are related. So this is the circuit diagram for the 3 omega method. As you can see, the heater and the thermometer present over there. It also needs a lock-in amplifier and a potentiometer, and all of this is connected to a computer where we can monitor the thermal conductivity, like whatever output that we are getting out of this entire system. So the problem statement is that, as it was mentioned earlier, that this method kind of only works with flat surfaces, or bulk solids which have flat surfaces. So so that is the issue. Like there is a geometric mismatch that rigid sensors cannot stick to curved surfaces or surfaces with a rigid texture or rugged texture, and it also causes air gaps, and because of air being present in the gaps, and air is a poor thermal conductor. As we can see, the conductivity is 0.026 watt per meter Kelvin. That's very low. So the trapped air kind of messes up with the measurements, and the goal, obviously, in the end, for the project is to eliminate the contact surface by ensuring a gap-free contact with the sample. So the solution to this problem is developing a flexible probe, a flexible thermal probe, which can kind of stick to uneven surfaces or surfaces which are not flat, curved surfaces. So the idea is that we create a substrate using polyimide or Kapton and PDMS to achieve a full conformal contact, and we can do it through fabrication by employing printed electronics principle to create thin film platinum heaters and electrodes. and what that is going to do is it will eliminate the air gaps, leading to negligible thermal contact resistance, which is what we want. So uh, we have to model the curved domain uh, to facilitate this thermal probe. So the analytical challenge here is to uh, take into consideration the curvature, because that is the main thing that we are going to be working on. And the assumption that we have to make is the thermal wave must not interact with the backside of the substrate or the macroscopic curvature. And this is the governing equation which we have to use to solve the cylindrical coordinates, because we are considering the surface to be a cylinder, even though if it is a very small surface, we are still using the assumption of it being a cylindrical kind of a medium. And we want the thermal penetration depth, the value of that lambda, to be as low as possible. That is what we are aiming to do here. So the design and fabrication methodology is that we create a flexible probe architecture. So the probe kind of has conformability and durability, and it is made using polymer materials. So the substrate material will be made using polyamide, which is Kapton, which I mentioned earlier, and the thickness has to be close to 50 micrometers. And we have used polyamide because of its high thermal stability and mechanical flexibility, which is what we want from that probe, for it to be flexible. And the active element is platinum, and we have used platinum because its stable nature and the linear temperature coefficient of resistance for platinum. And the design is going to be a 4-point probe configuration, and so this is the fabrication process. This is kind of like a flow chart that we are going to follow to basically construct the entire thermal probe, the flexible thermal probe. So the four stages are substrate preparation, patterning, deposition, and release. So in the substrate prep, the thin polyamide film is mounted on a rigid carrier and clenched to enhance adhesion so that it sticks properly. And in the patterning phase, we use photolithography to define the precise geometry of the narrow heater lines and wider contact pads, so that there's good surface area maintained during the contact. And in the deposition part, a thin adhesion layer of tin or chromium followed by platinum is deposited via sputtering process or evaporation. And in the last phase, for release and passivation, the probe is coated with a protective layer, which is Parylene C, and chemically released from the carrier, resulting in a freestanding flexible device. So for us to do this entire process, we have to do a simulation, a numerical simulation, or using MATLAB or Python, so that we can actually see if this entire process is going to work out with all the initial factors that we have assumed. So the governing model is for a 2D heat diffusion equation, and we'll do that using Python or MATLAB simulation. So as you can see here, the simulation was run with all the input values, and the color gradient demonstrates the thermal energy that is highly localized, which is like shallow penetration lambda, which is what I had mentioned earlier. For it to be as low as possible, the lower it is, the better it is. This thing, like the plot, it computationally verifies the high frequency approach, allowing us to safely treat the curved substrate as a planar. Then we have to extract the thermal conductivity, and for this as well, we use simulation, and I've generated a plot, and the value for K is around 5.627 watt per meter Kelvin, and the fit quality is strong because R square is greater than 0.98, and this is the governing formula with which we found the value for K, which is the extracted thermal conductivity at 5.627 watt per meter Kelvin. So the concluding part for this is, and the future work that can be done is that conformal contact was achieved, and high fidelity thermal measurement by ensuring conformal contact on curved surfaces was achieved using PDMS substrates, and model validation in which it confirmed that the high frequency operating regime allows for the accurate use of the planar heat diffusion equation. And in terms of performance, the probe demonstrated stable signal quality where R square was greater than 0.98, and the precise thermal conductivity extraction which we got to be around 5.627 watt per meter Kelvin. So the future aspects for this research are these 3 points where we can do anisotropy measurement, wherein we can integrate orthogonal heater elements to simultaneously measure in-plane and through-plane thermal conductivities. Or we can also integrate curvature quantification, where we can conduct systematic tests on various known radii to experimentally quantify the measurement error in highly curved regimes. And we can also look at temperature dependence, where we can expand the testing methodology to cryogenic and high temperature ranges to study temperature dependent phonon transport. Thank you so much. I hope you guys learned something from this entire presentation, and thank you for giving me the opportunity to present to you all. Thank you so much.